region of confusion, because there, by minimizing an individual Fi, you are not going to be able to tell what is the combined X star, that is all. And a very interesting thing happens now, just to gain some mathematical insight into that simulation that I showed you, that if you have a scalar x that is outside this region of confusion, which states that if you are far from the region within which an optimum can lie, so you are far away. So you've just started out your progress, you made a random initialization, most likely you're far away from where the solution is. So suppose that's where you are. What happens when you're in that far out region? So if you're in that far out region, you use a stochastic gradient of some ith component. So the full gradient will look like that. A stochastic gradient looks like just one component. And when you are far out, outside that min and max regime, then you can check by just looking at it that a stochastic gradient in that far away regime has exactly the same sign as the full gradient. What does gradient descent do? It says, well, walk in the direction of the negative gradient. And if far away from the optimum, outside the region of confusion, your stochastic gradient has the same sign as the true gradient, maybe in more linear algebra terms, it makes an acute angle with your gradient. So that means if even though a stochastic gradient is not exactly the full gradient, it has some component in the direction of the true gradient. This is 1D, here it is exactly